Welcome to today's deep dive. We're really glad you decided to join us today.
Yeah, absolutely. Thanks for tuning in.
Our mission today is a bit ambitious. I mean, we have taken a towering stack of technical documents.
Towering is right. It's a massive stack.
It really is. And I'm talking everything from dense academic papers on cryptography and consensus mechanisms all the way to the 2026 roadmaps for major networks like Ethereum and Solana.
Yeah, and we've even got that newly proposed SEC framework in the mix, too.
Right. And we're going to distill all of it into an engaging, accessible overview just for you.
Because, it's essential material. Blockchains are so often talked about in the mainstream as these magical trust machines.
The magic internet money.
Exactly. But underneath all the hype, they aren't magic at all. I mean, they were simply distributed systems relying on intense mathematics and some incredibly clever incentive structures.
Yeah, so today we are opening the hood to see exactly how this engine works. We're going to navigate the underlying cryptography, explore how a decentralized network actually agrees on the truth, and then look at the massive upgrades rolling out right now in 2026.
Say upgrades taking this tech to industrial grade scales, yeah.
Exactly. Okay, let's unpack this, starting with the absolute foundation. We know a blockchain is essentially a decentralized, distributed, append-only ledger.
Right.
But how does the network actually secure that data mathematically?
Well, the permanence of that append-only ledger relies heavily on our first cryptographic pillar, which is hashing algorithms.
Like a digital fingerprint.
Exactly like a digital fingerprint. Whenever data is submitted to the network, whether it's a single transaction or a massive smart contract deployment, it gets passed through this hashing algorithm, and the algorithm outputs a fixed length string of characters.
And looking at the academic papers we reviewed, they mentioned 3 specific technical properties that make a hashing algorithm actually suitable for a blockchain. I know they cited SHA-256 for Bitcoin and KEKAK-256 for Ethereum, but can you walk us through those 3 required properties?
Sure. So the first property is pre-image resistance.
Okay.
This basically means the hashing process is fundamentally a one-way street. It must be computationally infeasible to take the resulting hash and somehow reverse engineer the original data from it.
But you can't unbake the cake.
Exactly. You can't unbake it. The second property is second pre-image resistance. This guarantees that if you have a specific piece of data and its hash, you cannot find a different secondary piece of data that somehow produces that exact same hash.
Which prevents someone from, say, secretly swapping out transaction details while keeping the block's hash intact.
Precisely. You nailed it. And the third property is collision resistance. It must be exceptionally rare, practically impossible, really for any 2 entirely distinct random inputs to ever collide and produce the same hash output.
Got it. And these hashes are then used to chain the blocks together, right? With every new block embedding the hash of the preceding one.
That's the chain in blockchain.
Now, the sources also spend a lot of time on something called Merkle trees in this context. It seems like a way to optimize how these hashes are stored, rather than just listing thousands of transaction hashes sequentially in a block.
Yeah, Merkle trees are a brilliant structural optimization. Instead of a node having to download and verify every single transaction in a block linearly, a Merkle tree takes all those transactions and pairs them up.
So it hashes them together.
Right. It hashes each pair together, then takes those resulting hashes and pairs them up again. And it just repeats this process upward until you are left with one single hash at the very top.
Which is known as the Merkle root.
Exactly. The Merkle root.
So if I want to verify that my specific transaction is in a block, I don't need the entire block's data. I just need my transaction, its direct path up the tree, and that root hash.
That is the beauty of it. It allows for incredibly efficient verification. It significantly reduces the bandwidth and storage required for the nodes.
Okay, but hashing only secures the integrity of the chain itself.
Yeah.
To actually prove you have the authority to move digital assets, the network relies on asymmetric cryptography,
Right.
which is the public and private key infrastructure. From my understanding of the research, your public key acts as your address on the ledger, which is visible to anyone.
Like a mailbox.
Like a mailbox, yeah. But your private key is the actual cryptographic tool you use to authorize actions.
And that authorization is executed through a digital signature. When you initiate a transaction, you sign the transaction's hash with your private key.
And the network checks it.
Right. The network uses your public key to verify that the signature could only have been generated by the corresponding private key. This fundamentally solves the double spend problem without needing a centralized bank.
And it also guarantees non-repudiation.
Yes. Non-repudiation is huge. Once the math proves your key signed the transaction, you cannot credibly deny having sent it.
So we have hashes ensuring data integrity and asymmetric cryptography handling ownership. But here is the massive challenge the documents focus on next. How does a global network of decentralized strangers actually agree on the state of this ledger? Who gets to append the next block?
That is the classic problem of consensus. Now, the original method, pioneered by Bitcoin, is proof of work. In this model, nodes or miners compete to solve a computationally intensive mathematical puzzle.
And the first one to find the solution earns the right to add the block.
Yeah,
And gets a reward.
exactly.
One of the papers points out that proof of work natively solves the nothing at stake problem.
It does.
Because miners are forced to burn real-world electricity to compute these puzzles, they are economically incentivized to point their hardware exclusively at the most valid dominant chain. If they try to split their computing power to mine on multiple different forks of the network at once,
They just dilute their hash rate.
right, they dilute it and drastically reduce their chances of winning any reward at all.
It anchors the digital truth to physical energy expenditure. But as the industry has recognized, that physical energy burn is immense,
Massive.
which has driven the major shift toward proof of stake, where instead of burning electricity, validators lock up or stake their native tokens as collateral to participate in consensus.
Here's where it gets really interesting. Let's dig into Ethereum's specific proof-of-stake architecture. The documents refer to it as Casper FFG, and it seems to completely rewrite the rules of how nodes reach agreement compared to proof of work.
Casper FFG is honestly a masterclass in protocol design. Its effectiveness hinges on two major mechanisms: the two-phase commit and accountable safety.
Okay, let's break that down.
To grasp how it functions, we have to look at how Ethereum measures time. The protocol divides time into continuous chunks called slots, and it groups those slots into larger windows called epochs.
So how does a block of transactions actually become permanently recognized as the truth within these epochs?
It takes 2 full epochs to finalize a checkpoint on the chain. During the first round, validators broadcast their votes on what they see as the most accurate recent checkpoint.
Okay.
If a supermajority of the network agrees, that checkpoint reaches a state called justification.
Justification, right.
Then in the second round, validators essentially vote to confirm that they saw the previous justification. Once a supermajority agrees on that second round, the checkpoint reaches finalization. At that point, the data is permanent.
But in proof of stake, validators aren't burning expensive electricity to cast these votes. What prevents a validator from just voting on every possible fork of the chain simultaneously to guarantee they end up on the winning side?
That exact vulnerability is what Casper's accountable safety is designed to solve, and it does so through a mechanism called slashing.
Flashing.
Yeah. The protocol has strict rules like the no double vote rule, which prevents voting for 2 conflicting checkpoints at the same height, and the no surround vote rule, which prevents voting in a way that contradicts previous commitments.
And if they break the rules?
If a validator violates these rules, the network algorithmically detects the cryptographic proof of their conflicting votes and permanently confiscates a massive portion of their staked collateral.
The research papers provided an incredible analogy for this cascading consensus logic. They referenced a famous logic puzzle called the Blue Eyes puzzle.
Oh, I love that one.
Yeah, can you walk us through how a logic brain teaser actually maps to how computers agree with each other?
Sure. So the Blue Eyes puzzle involves an island of people who all have blue eyes, but nobody knows their own eye color, and they are forbidden from communicating.
Okay.
If a visitor arrives and simply states, "I see someone with blue eyes," it sets off this cascading logical deduction. Everyone knows the visitor's statement, but more importantly, everyone knows that everyone else knows the statement.
It creates common knowledge.
Exactly. In Casper FFG, it is not enough for a validator to individually verify a block. The protocol requires cryptographic proof that a supermajority of other validators have also verified it, and proof that those validators know the rest of the network agrees with them.
It's mind-bending to think about computers constantly verifying that other computers have verified the verifications.
It really is. But this raises an important question, though. What happens when this complex choreography is actively attacked?
Right. The documents outline several nightmare scenarios for developers. The most universally understood threat is the 51% attack.
Yeah. If a single entity manages to acquire control over the majority of the network's consensus power, whether that's computational hash rate in proof of work or total staked tokens in proof of stake, they essentially dictate the truth.
They can censor transactions, rewrite recent history, and execute double spends.
Exactly.
We also saw mentions of civil attacks, where an attacker creates thousands of fake identities to overwhelm the network. But there was one vulnerability detailed in the academic papers that is entirely exclusive to proof of stake.
The long-range attack.
Yes, the long-range attack. And it relies on two concepts: costless simulation and weak subjectivity. How does a long-range attack actually work in practice?
So in a proof-of-work system, an attacker trying to rewrite years of blockchain history would have to literally outcompute the entire world's energy expenditure over that time frame, which is practically impossible.
Right.
But in proof of stake, generating historical blocks doesn't cost physical energy. It is just a computational simulation.
So an attacker who held a massive amount of staked tokens, say 3 years ago, could go back to that point in the chain's history, sell off their current tokens on the real network, and then privately simulate a completely alternate timeline from that point forward.
Exactly. And because it is merely a costless simulation, they can generate millions of fake blocks in a matter of minutes on their private servers. They can forge an entirely divergent branch of the blockchain where they never sold their tokens. And eventually, they broadcast this massive alternate history to the network, claiming it is the true chain.
But how would the network ever fall for that? Wouldn't the nodes just look at the math and realize it's a fabricated timeline?
That is where the concept of weak subjectivity comes into play. A node that has been continuously online would instantly reject the attacker's fake chain because it has been tracking the real chain's finalized checkpoints all along.
Right.
But imagine a brand new node booting up for the very first time, or a node coming back online after being offline for a year.
Oh, I see. They wouldn't know which long chain is the legitimate one just by looking at the cryptographic weight.
They wouldn't. The math alone isn't enough anymore. In proof of stake, a newly syncing node must rely on recent, trusted checkpoints shared by the community, often retrieved from block explorers or trusted peers to know which timeline is reality.
That is a fundamental shift in security philosophy compared to proof of work.
A massive shift.
So what does this all mean for you, the listener, right now in 2026? We've gone through the underlying theory and the terrifying vulnerabilities, but the roadmaps for the major networks show a huge push toward industrial-grade execution.
They do. The 2026 landscape is defined by major structural overhauls. Let's look at Ethereum's roadmap. They have basically abandoned the strategy of massive, infrequent updates that carry huge execution risks. Instead, they are deploying smaller, highly targeted upgrades. In the first half of 2026, they are rolling out an upgrade dubbed Glamsterdam.
Glamsterdam.
Yeah, it's intensely focused on execution layer efficiency and optimizing gas limits.
But the upgrade that really caught my eye is slated for the second half of 2026. It is called Higota.
Higota, yes.
And the primary goal is tackling state growth by implementing something called Merkle trees. Now, we discussed Merkle trees earlier, so how do Merkle trees fundamentally change the architecture?
Well, state growth is arguably Ethereum's most existential threat right now. The ledger is simply getting too massive for regular consumer-grade hardware to store.
Right.
Merkle trees address this by replacing the traditional hash functions used in Merkle trees with advanced cryptography called vector commitments.
How does a vector commitment reduce the storage burden?
In a Merkle tree, providing a cryptographic proof requires passing along all the sibling, hashes up the branches of the tree, which takes up a lot of data bandwidth. Merkle trees, using vector commitments, allow for proofs that are exponentially smaller.
Really?
Yeah. A node can verify an immense amount of data with a remarkably tiny cryptographic proof. This paves the way for stateless clients.
Stateless clients, meaning nodes that can verify the entire blockchain without having to store the terabytes of historical state data on their hard drives.
Exactly.
That is a massive leap for decentralization if anyone can run a node from a standard laptop again.
It's huge.
Let's pivot to Solana. Their 2026 upgrade is called Alpenglow, and the scope of it is startling. They are completely tearing out proof of history, the consensus mechanism the network was practically built on.
And replacing it with a new dual component system called voter and rotor.
Yeah. How does that work?
Voter handles the consensus voting logic, while rotor is entirely dedicated to optimizing block propagation across the global network. And the stated goal of Alpenglow is to drive finality times down to roughly 100 to 150 milliseconds.
Wait, 100 to 150 milliseconds.
Yeah.
How is that physically possible when you factor in the speed of light and basic network latency? across globally distributed validators.
It sounds physically impossible, which is why it requires such a massive structural overhaul. Rotor essentially pipelines the data propagation. Instead of waiting for a full block to be packaged and sent, shreds of data are continuously streamed and validated in parallel across the network.
Ah,
By decoupling the voting from the data streaming, they are trying to push consensus to the absolute physical limits of fiber optic cables.
that's incredible. Now, while Solana pushes for speed, the research highlights BNB Chain's 2026 focus on scaling their Ethereum virtual machine performance to handle enterprise-level throughput. And Polygon is taking a totally different approach with their AG layer. From the documentation, it sounds like an attempt to make the fractured landscape of different blockchains feel like one cohesive network.
The AG layer utilizes zero-knowledge proofs to cryptographically unify liquidity across various disparate chains. If you are a user interacting with a decentralized application, you shouldn't have to worry about bridging assets manually or dealing with different network fees.
AG layer abstracts all of that complexity away.
Exactly. The zero-knowledge proofs confirm the validity of cross-chain transactions instantly, making it feel like you are operating on a single, unified database.
It is all about making the underlying cryptography invisible.
Yes.
And speaking of making the tech invisible, the research papers provided incredible case studies of real-world integrations happening right now. Let's break down the supply chain architecture they highlighted.
The supply chain model outlined is a perfect example of hybrid architecture. It doesn't put everything on a public blockchain. It starts in the physical world with IoT sensors.
Tracking things like the temperature of a shipping container or the humidity of a warehouse.
Right.
But the sensors aren't writing data directly to the blockchain, right? That would be far too expensive and slow.
Correct. The raw data stream feeds into an edge processing layer. This local computing layer filters the noise, identifying only the critical events, like if a temperature drops below a safe threshold.
Makes sense.
Once a critical event is flagged, it is sent to Hyperledger Fabric, which is a permissioned enterprise-grade blockchain layer.
And from Hyperledger, the data state can trigger automated smart contracts to release payments or issue alerts. But what about the actual heavy sensor logs? Where do those live?
They use a hybrid storage approach. The bulky raw data files are stored off-chain using a combination of MongoDB for structured querying and IPFS, the interplanetary file system for decentralized file hosting.
Okay, so what goes on the blockchain?
The blockchain merely stores the cryptographic hash of those files to prove they haven't been tampered with. Finally, the human operator at a logistics company just logs into a clean, intuitive React.js user interface. They never see a hash or a private key. They just see an immutable, real-time dashboard.
That level of integration is how this technology quietly becomes the backbone of global commerce.
Absolutely.
But perhaps the most impactful document in our entire stack today was the newly proposed SEC framework for 2026. This framework bridges the gap between traditional regulatory compliance and cryptographic automation, specifically focusing on the tokenization of sovereign debt.
If we connect this to the bigger picture, this regulatory framework is attempting to solve the last-mile problem of global financial inclusion. Historically, investing in sovereign debt or high-yield institutional assets required massive capital minimums and a web of expensive intermediaries.
But by tokenizing those assets on a blockchain, the SEC framework is establishing standardized rules for fractional ownership. According to the documents, the minimum investment threshold for these sovereign debt tokens can drop to anywhere between $25 and $100.
It democratizes access entirely. However, to authorize this at a regulatory level, the SEC framework imposes strict architectural mandates. It requires highly optimized, user-friendly mobile interfaces to protect retail investors from the technical complexities of self-custody.
Right.
It also demands robust API architectures to ensure seamless fiat-to-crypto settlements with traditional banking infrastructure.
The component of the framework that fascinated me most was the mandate for explainable AI. It seems regulators realize that if compliance and asset tokenization are going to be managed by automated smart contracts and AI agents, those agents can't operate in a black box.
That is a critical regulatory hurdle. The explainable AI mandate requires that any automated system making decisions regarding asset compliance, KYC verification, or liquidity provisioning must be able to output human-readable logic.
So they have to show their work.
Exactly. If an algorithm flags a transaction or restricts a token transfer, regulators need to be able to audit the precise decision-making tree that led to that action. The cryptography ensures the data is secure, but the explainable AI ensures the operational logic is transparent and legally compliant.
It's incredible to step back and synthesize the journey we've been on today. We started deep in the technical weeds with the one-way mathematics of hashing algorithms and the digital signatures of asymmetric cryptography.
We covered a lot of ground.
We really did. We navigated the complex cascading logic of nodes reaching consensus through Casper FFG and explored how concepts like weak subjectivity open the door to long-range attacks. And we follow that thread all the way up to the reality of 2026.
Network upgrades pushing transaction finality down to milliseconds through sheer architectural innovation.
And SEC frameworks utilizing explainable AI to open up global sovereign debt to anyone with a smartphone and $25.
We are witnessing the transition of blockchain from an experimental theoretical computer science project into the foundational infrastructure of the modern financial system.
We truly are. And as we wrap up, I want to leave you with a final provocative thought to mull over. If blockchains in 2026 are successfully achieving near-instant 100-millisecond finality, and if regulatory frameworks are standardizing the fractional ownership of massive financial assets directly through mobile applications, what does the traditional concept of a bank look like in a decade?
That's the billion-dollar question.
Exactly. If the concept of trust is completely automated by cryptographic proofs and global liquidity is natively unified by zero-knowledge protocols, will the banks of the future simply be software interfaces running on top of decentralized nodes?
It is a profound structural shift to consider for the future of finance.
It absolutely is. Thank you so much for joining us on this deep dive. We hope it helped demystify the engine running underneath the blockchain ecosystem. Keep learning, stay curious, and we will catch you next time.